What we're going to talk about this afternoon is, as the title would suggest, the art of Java-type patterns. And this is something which has become a lot bigger in Java, really since about JDK 12, I guess, maybe JDK 14. The introduction of pattern matching in Java. But we're not talking about pattern matching like regular expression pattern matching. So it's not just simply using the, regex and things like that. What do we mean by patterns then in this particular situation? Now, patterns have been around for a long time. In fact, you can go all the way back to the 1960s and you can look at languages like Haskell or Awk. Anybody used Awk? Oh, good. A few older people here. Excellent. So, and of the bonus points, anybody know what Awk stands for? No? Okay. Aho, Weinberger, and Kernighan. Brian Kernighan, who was one of the people who invented the C programming language. But anyway, I digress. So pattern matching has been around for a long time. And what we mean by a pattern in this context is something that consists of two things. The first is what we call a match predicate. A predicate is something that evaluates to true or false. And so what we're looking for is something that we can determine we match against that. And that's a target that we're looking for. And we'll see plenty of examples of this as we go through. So you'll get a feeling for what we mean by a match predicate. And then the second thing that we get associated with the match predicate is 0 or more pattern variables. And the pattern variables are what we're going to use, conditionally extract them, and then use them based on what we've done with the predicate in terms of matching or not matching. So it might look complicated, but it's actually very simple. And we'll see lots of examples of this as we go through. Now, before we get into the pattern matching, we need to talk about a couple of other things that have been introduced into Java because they're very closely related and make a lot of patterns. So let's talk about a couple of things. And the first of those is switch expressions. Now, if we look at Java programming language, it was very heavily based in terms of the syntax on the C programming language. One of the things you have in C is a switch statement. And the switch statement is designed so that you have different cases which you can match against. And then if you match against a particular case, you do whatever is in the body of that case. We're all familiar with this, aren't we? And the important thing about that is the design says that if you match on a particular case, you execute code that's associated with that case or case block. If you do not put a break in, you will drop down into the next set of cases. So here is a question for you. Who here has ever forgotten to put a break statement in their switch? Yes, pretty much everybody. I've certainly done this. And this is one of the things about switch is that it's somewhat error prone. Like I said, the fact that you can forget to put the break statement in and it will behave very differently to the way you expect it to. And that can make debugging that kind of code very difficult. Also, there's some limitations around the way that we scope variables. It's not always intuitive when you're doing that kind of thing. So let's look at an example of a switch statement. And this is a very common way that we use switch, which is to say, let's switch on one variable, then assign a value to another variable. Here, I've got the switch on the day of the week, and I've got the number of letters which I want to assign. Clearly, the code is very straightforward. I do case Monday, case Friday, case Sunday, set the number of letters to be 6, remember to put the break statement in, and get a value that I don't expect, and then do everything the same for different days of the week. And if I got something I don't recognize, I throw an exception. All good. The other thing that's error prone about this is that if we forget, this is going to be interesting, if we forget to assign a value to number of letters. Now, if number of letters is an instance field rather than a local variable, the compiler won't care about that. It'll simply say, well, the instance field has a default value of 0, so I don't care if you value for it. So it makes this very error prone. What we've done in JDK 12, so going back quite a long way now, is introduce a switch expression. Now, statement executes a set of instructions, but doesn't generate a return value. An expression executes a set of statements, but does generate a return value that can be assigned to a variable. If we look at this code, we can see now that it's a lot simpler in terms of the number of lines than we had previously. The great thing about it is that we don't lose any of the readability that we had before. So we can still see exactly what's going on. It's not any more dense than it was before. Now we have an expression which returns a value. And that means we only need to make the assignment to number of letters once, and the compiler could potentially check that if they wanted to, but we know that we only make that assignment once. Within the switch expression, we've got our cases as we had before, but now the developers have discovered this very cunning thing that nobody ever knew about before. It's called a comma-separated list. And so now, rather than having to have separate lines for each case, we can put them on the same line, reducing the number of lines of code dramatically. How did it take us 25 years to figure that one out? That I don't know. Then we borrowed some syntax from the Lambda expressions. We use the arrow, and the right-hand side of the arrow is the value that we're going to return from the switch expression, or if we have a default, we throw a new illegal state exception. The compiler can check that there is always something to return, and it's of the right, and it can check that if it's not a return, it's an exception being thrown. So we can make more compile time checks rather than runtime checks. Much better for reliable code. Now, the other thing about switch expressions is they have to be complete or exhaustive, and we'll come back to what this is later on. Right, the other thing we need to talk about before we get into patterns again is algebraic data type. What do I mean by this? Well, here's an example of a class that we write very frequently. It's just an encapsulation of simple data. Java is object-oriented, so we create a class, in this case called point. As we can see, what we want to do is encapsulate two double variables, x and y. So we have to have two instance fields called x and y. We then have to have a constructor, which we pass parameters to. We need explicit code, which says assign the values of the parameters we pass to the instance fields. And then because we've made them private, we need accessor methods to allow us to retrieve the values x and y. So we've got double x and double y there. All of this is like 14 lines of code just to create a tuple. And I must admit that I did talk to Brian Gertz about this when we were doing this kind of stuff. And I said, why don't we have a tuple in Java? I mean, we've got 4,500 plus classes in Java in the standard libraries. Why don't we have a tuple? And he said, yes, we could give you a tuple, but then you'd want a triple, and then you'd want a quadruple, and then you'd want, and where do we stop? So they found a better way of doing it. And what they did was they said, let's introduce records. JDK 14, we got the idea of a record. Now, a record is just a class. It's just a slightly special form of class in the same way that enumeration is a slightly special form of class. What we do here is we provide a record declarator which says, use the keyword record to indicate that we have got a record. We'll give it a name, point, so it's the same as our class, and we'll use the same syntax as the constructor to indicate what values we want to store in our record. So double x and double y. And then because it is like a class, we have the braces as we would normally do, but there's nothing in the body of the class. The compiler does all of the hard work for us in terms of generating the constructor, generating the accessor methods, and so on. So it makes our code, as you can see, go from 14 lines of code to 1 line of code much nicer, much easier to use. Now, a couple of other things about records is that because they are just classes, you can also make them generic. So we could add a generic type parameter to this, and we could say anything of type T, store objects of type T in our record. The other thing we can do is we can add more functionality to our record. It's a class, so we can add methods to it to give it behavior, and we can add static instance fields so that we've got values that we can use. We can't add any more instance fields that are not static because we can only use ones that are in the record declaration. In this case, I've got a circle, has a single value that we're storing there, radius. I've got a static field, which is the value of pi, And then I've added a method here so that I can retrieve the area based on the radius and calculating it with pi. So it gives us a lot more flexibility in terms of how we can use records rather than just being storage of data. We can add additional behavior. Last thing to talk about before we get into patterns is a little bit about inheritance in Java. So Java, again, object-oriented, and it has the idea of inheritance. So we can declare a class type hierarchy here where we've got a shape as the superclass, and then we've got three subclasses, triangle, square, and pentagon. Now, the drawback to this is that we don't have any real control over who can inherit from these classes. The only thing we can do is to mark a class as final, in which case nobody can inherit from it. If we don't do that, anybody is free to inherit from our class. So in JDK 15, we introduced the idea of sealed classes. What this says is that you can now specify a list of classes that are allowed to inherit from that class, and only those ones will be allowed to do so. So we now have this syntax here. So we say public, and then we add modifier sealed class shape, add a permits clause, which tells the compiler only triangle, square, and pentagon are allowed subclasses. Everything works quite happily in our code. If somebody would come along and say, oh, I like that shape class, I want to have a circle as a subclass of that. Because it's not declared in the permits clause, the compiler will say, no, you can't do that. Class is not allowed to extend sealed class shape. It's not listed in the permits clause. So you've now got restrictions over what you can do there. And that gives us the idea of constricted type hierarchies. Right, let's get on to the pattern matching side of things. Now, the first place that we can use pattern matching is where we use the instanceof operator. Java, being object-oriented, has polymorphism. Polymorphism basically says that you can view an object as any of the types that it implements. Now, that's its concrete class, any of the superclasses of that, all the way up to object, and any of the interfaces which any of the classes which it implements, inherits from, implements. So you can view it as any of those types. But if you want to determine if a particular object is of a particular type, then you use the instanceof operator. You know, we all know about this. We've done it before. And this is the kind of way that we do it. We say if obj instance of string, and then within the body of that if statement, we have to do a line here, which is saying, make an explicit cast of obj to type string and assign it to a new variable called s of type string. Now, that's really a bit redundant, isn't it? Because you could say justifiably that within the body of that if statement, within the true branch here, we know that obj is of type string. So wouldn't it be obvious to just treat obj as a string in that case and be able to reference it as a string? But that's not the way that Java works. And the solution that they came up with to make this easier was pattern matching, or instanceof. Here we have a slight change on what we had before. So now we've got if obj instance of string. Now remember I said that pattern consists of a pattern predicate and pattern variables. So here, our pattern predicate, what we're evaluating to see if it's true or false, is obj instance of string. If that evaluates true, then we have a pattern variable s, and we will assign object obj to s as a string. So we don't have to put that explicit cast and explicit assignment in there. Within the true branch of the if statement, clearly we do have a string, so we can reference s and we can call the length method on that to get the length of the string. But if we tried to use s in the else branch, because we haven't matched the predicate, we don't have the s in scope, and so we can't use it. Very logical. But we can extend that a little bit further, and we can say if obj instance of string and put a test after that to say is s.length greater than 0. Now this will work quite happily because we know the way that the AND operator works is to always evaluate the left-hand side of the operator, and only if that evaluates true, do we evaluate the right-hand side of the operator? So if we evaluate the left-hand side of the operator and it evaluates the true, we know that we have a string, so S scope and is valid. So the right-hand side, try to call s.length being greater than 0, it will work quite happily and the compiler can do that. If, however, we were to try and do the same thing with an OR, that wouldn't work. Because, again, we know that the OR operator, we always evaluate the left-hand side of the operator. If that evaluates if that's false, then we evaluate the right-hand side of the operator. So if it evaluated false, we don't have a string, so the scope of S is not valid, and therefore we can call s.length on the right-hand side, and it wouldn't work. The compiler would reject that. Just a little bit more about pattern matching here. The scope may not necessarily be obvious, because we can invert the test, and we can say, in this case, if not O instance of string S, return. So that will say that if we don't have a string, we return. After that, until we exit the method, the scope of S will be completely valid, and so we can use it anywhere we like. We're not limited just within that if block. And this brings us to quite an important part about the binding variables and the scope of those variables, which is the way that scoping works. If we look at local variables, the way local variables work is that the scope of them, where you can use them, is from where they're defined until the end of the block of code in which they're defined. Now, that could be a method, it could be an if statement, it could be a for loop, a while loop, or even just a set of braces. So that defines the scope. But it also, in the case of local variables, is that they are subject to definite assignment. You have to assign a value to a local variable, otherwise the compiler will reject it. There is no default value as there is with instance fields. Now, when we look at the binding variables, which are the pattern variables, they also have scope, but their scope is where they're subject to definite assignment. Where they will have a value is where you can use them, which is kind of logical, but that's the way it works. So it uses flow scoping. So only where they're valid is where you can use them. But it means that the scoping of pattern variables or binding variables is different to the scoping of local variables. To give you an example, we can do this. If O instance of integer, we do something. Else if O instance of float, reuse the same variable name, do something. Else if O instance of long, reuse the same variable name, num, and then do something. Now, we couldn't do that if we were using local variables, because the compiler would say, well, you've already used num in one place, you can't use it in a second place. So the scoping here is limited to only the true branch, because that's where the scope is valid. So we can reuse the num in 3 different places, and that makes our life easier because we don't have to think of lots of different variable names. So I just like that. Right, so here's a puzzle for you. And I'm going to include several puzzles in this presentation. Piece of code, object S. So I'm creating a variable called S of type object and instantiating a new object. Wonderful. And then I say if S instance of string S, so I'm using pattern matching, print out the length of the string. Else, print out no string. Then. So now here we've got a little bit of a problem, you see, because I've used S for the name of my object, and I'm using S for the name of my pattern variable. So I'm going to give you 3 options as to what can happen here. 1, the code will work. Option 2, the code will not compile. And option 3, the code will not compile, but it will work. Aha, right. So we're going to have a vote. Who thinks the code will work? Okay, a few people. Who thinks the code will not compile? Yes, more people. Who thinks the code will compile, but it will work? Nobody. I mean, come on, it's the obvious one, isn't it? I mean, really. Okay, anyway. So the answer is that the code will not compile. So if we put this into our IDE, if we put it into IntelliJ or whatever, and we try and compile this, what we'll see is an error message here, Java C, and it will say, no, can't do that because variable S is already defined in method main. So you look at that and you think to yourself, well, okay, that's great. So how is that a puzzle? Well, the puzzle is that the code will also work. Because if you do it in JShell, and I literally have typed out, and I checked it with JDK 23 just recently, just to make sure that I haven't lost any of my things in my presentation. If you do this in JShell and you create a new object, it says, you've got a new object. If you type this in, it will say, no, it's not great. I have no idea, absolutely no idea why that works. What's more interesting is I have presented this to several of the engineers at Oracle who work on this stuff, and they have no idea why this works. They keep telling me it's a bug, but nobody fixes it. So, right, next thing, pattern matching for switch. So if we look at the switch expression and the switch statement that we saw before, previously we've been limited on what we can switch on. So we can switch on integral values, so numbers, we can switch on strings, and we can switch on enumerations. And these are things that have been introduced over time since like JDK 7 and so on. What we've now done is expand the switch so that we can actually match on a type pattern. What we can do now is something like this. So we'll do a type tester method, which we'll pass an object into, and then we'll switch on O. And then we're going to have cases for different types. Now, the first thing is that we now have the ability to put a case for null in there. And that's very nice because previously we would have had to have a separate test outside of the switch to see if we had a null to catch that before we did the switch. Now we can actually put the case for null in there and deal with it explicitly. Then we can have cases for specific types, case string, case color, and these again are pattern predicates. So case string is where we're matching against a string. And then we have a pattern variable, S, which will be assigned if we match, or C for color, if we match against that. And then if we do, we have something that happens on the other side to say we're going to print out string or print out null type or whatever. Now, primitives are net objects in Java, not true objects. So you can't, well, you can, but later. You can't have a case on a primitive, but you can have a case on an array of primitives. So you can do a case int array IA and print out the length of it. And then you have it default as well. So now we have the ability to actually do things like that. Now, null is a little bit special. So just mention a couple of things about this. So the case null can be used in all switch statements and expressions. If you don't include it, the compiler will insert one for you. So this is necessary for backwards compatibility. You wouldn't necessarily kind of think about this straight away, but it is true. This is what happens now. If I have a switch like this, where I'm only catching string, color, int array, or anything else, if I pass in a null to that, what I actually get is a null pointer exception. So to get that to work, the compiler will effectively insert this line for me at the beginning to throw a null pointer exception. So the behavior in this case is the same as it would have been before we had the ability to put a null in there. Now, you can also null at the bottom and combine it with the default, because remember, we can do comma separated lists now, and that means that you can handle null and a default situation in the same case. So again, nice little extra thing to make your life easier. Completeness. Right, so I mentioned this earlier on, that we need to have completeness for our switch. What does this mean? Well, what we have to do is we have to deal with all possible types that can be passed to the switch. Here I've got an example where I'm doing switch on O, but I've got a case for string and I've got a case for integer. What happens if I pass a color object in, or a float, or basically anything else? Well, you could argue that because there isn't a match for anything which isn't a string or an integer, then you simply ignore it and you bypass that switch and continue with the code after that. But the designer said, well, that's going to introduce too many potential errors. So what we need you to do is to guarantee that all the possible types are handled. Clearly, in this case, if you wanted to handle all possible types, you couldn't do it explicitly because there are infinite types, so you would have to have an infinite number of cases. The way to get around that is very logically just to add a default. That means that if it's anything but string or integer, then it will be caught by the default case. But it does mean that in this situation, you do have to add a default. Now, it doesn't mean that you have to have a default in all situations. If we think back to the previous sealed class example I gave you, so we had a shape, which had 3 subclasses, square, triangle, square, and pentagon. So in that case, it's a sealed type hierarchy. There are only 4 possible classes that can exist in that hierarchy. So here we can define a switch on shape and have case triangle, case square, case pentagon, and case shape. That will catch absolutely everything. So we do not have to have a default because there isn't anything which would be caught by the default. All of the possible things that we could pass to that will be caught by that case, those cases. So the switch will work and it is complete. Now, the other thing that we can do is we can extend the switches and the cases to include what's called a guard. So we're going to have a guarded pattern. And this is similar to the example I gave you when we were talking about pattern matching with instance of, where you can do if something is an instance of type and then call the pattern variable with a method and test against it. So we can do the same thing in our switch with pattern matching. Interestingly, the designers of this, initially, they used the double ampersand in the same way that we would do for instance of. So we would have case triangle T and T.area is greater than 25. But then they decided that they wanted to make it more readable, I suppose. And they said, rather than using double ampersand, the AND operator, we will use a new keyword that we'll introduce called when. So now we have case triangle T when T.area is greater than 25. And I'm not convinced that's a great idea. And I'll show you why in a moment. But we can have the guarded pattern there, and we say if it's greater than 25, then we do that. And if it's just a triangle on its own, then we've got a small triangle and everything works in exactly the same way. So essentially, the syntax of that is to say you've got your primary pattern, then you have the keyword, and then you have a conditional and expression. Only works for patterns, so you can't use it in a normal case. So where you've got a constant, case foo, for example, you can't then say when something else. Pattern dominance is another thing that you need to be aware of. So let's reorder the things that we have in our switch here, and let's put the shape at the top, and then triangle and square and pentagon. So what's wrong with this? I think I hear the right answer. The right answer is that obviously shape is the superclass of triangle, square, and pentagon. And as we know, polymorphism says that we can view any shape object as a shape. So what will happen is that every single thing that we pass into it will be caught by the case for shape, and we will never get triangle, square, or pentagon. That makes the code inaccessible, and so what will happen is we'll say this case label is dominated by a preceding case label. Actually, it's the red one, which is the one that's dominating. It'll be the ones below it that will actually generate the error. So yeah, shape is always matched first. Triangle, square, and pentagon case are unreachable. Right, in this case, we also need to be careful how we do things with a guarded pattern. So we can say case triangle T, print out a big triangle, case triangle T when T.area is less than 25. This will still not work because, of course, all triangles will be either, well, we'll just match against triangle. We won't have to test the area. So we would always match against triangle, and we would hide the code for the guarded pattern. So again, that will dominate the guarded pattern. However, what about if we do this? Right, so now we're going to have guarded patterns. We'll say if case triangle T when T.area is less than 100, we've got a small triangle. Triangle T when T.area is less than 25, tight triangle, and then case triangle T, we've got a triangle. So who thinks that will compile? Because, technically, you could say, well, if the area is less than 100, so 12 is less than 100, is also less than 25. So anything that's less than 25 will match on the less than 100. So, okay, let's have a show then. Who thinks this will compile? Well, oh, God. Okay. So we've got a few people who think this will compile. And the answer is yes, it will. The compiler only tests against the type and the guarded pattern. So it will look to see whether you've got a guarded pattern after an unguarded pattern, but it doesn't have the ability to then delve deeper into the code and try and figure out, well, actually that guard will dominate that guard. So it will only look at whether you've got an unguarded pattern before a guarded pattern and generate an error there. So this won't generate an error. Say again? What it'll print is always a small triangle, because if you pass 12 in, it will always match with less than 100. But the compiler won't care that it wouldn't possibly match against less than 25. Well, I deliberately didn't make shape abstract. So you can instantiate shape, in which case it's not a triangle, it's not a square, and it's not a pentagon. Therefore, it would then match against the shape. Yeah, if it was an interface or an abstract type, then you wouldn't need the shape at the bottom. And in fact, you kind of stole my thunder there a little bit, because the next one is we can actually remove the triangle completely. And if we remove the triangle completely and only have two guarded patterns, this will still work quite happily. Why will it work? Because shape is the superclass of triangle. So even though we've got guarded triangle patterns here, the fact that we don't have a triangle unguarded pattern, the compiler won't complain because it knows that it can match a triangle against shape. So that will still work. So yeah, what happens if we call shape test with triangle 200? Obviously the answer to that is we get a shape. Yes. Well, okay, this is where I get into the sort of when. Okay, so where when is important. Let's create some code. So we'll have an abstract class. So abstract class this time, which is called interrogator. And the interrogator abstract class will have a number of subclasses because we're sealed, and it will have subclasses which are who, what, where, when, and why. Then we're going to create a class called when, which extends interrogator. So that's the subclass that we want, which is going to have a public method called when in it. You can see where I'm going with this, can't you? Then what we can do is we can actually set up test question, which takes an interrogator, and then we'll switch on question. And clearly we can have certain cases. I haven't made it complete yet, but we've got case what, case where, case why, and then we'll have a default, even though we don't need one, how, because we don't know how we would actually possibly get there. And then we actually define a couple of extra methods outside of that just to be complete, and have a Boolean which is called where and a void called why. What we can then do is we can add another line to this, which is case who, what, where, when, who, what, where, why. And obviously what's happening here is we're using the pattern is to match against the type who, but then we'll give it a pattern variable called what. We'll then use the when to indicate it's a guarded pattern. We'll then use where to evaluate whether the guard evaluates to true or false, and if it does, we will call why. So this will all work quite happily. Who can guess what the next one is? Yep. Case when. Now this will work. This will work quite happily, because what we're doing here is we're saying the type is when, the pattern variable that we're giving to it is when. We're then using the when to indicate we've got a guard. We're then going to use the when as the pattern variable and call the when method on the reference to the pattern variable. And if that evaluates true, we'll then call the local method when, which we've declared down here, which returns void. So that will compile quite happily. This is why I don't really like using when, although I would really recommend don't write code like this. This is not good code in Java, but it is fun to do. And what I would say is that the use of when as a keyword is what they call a contextual keyword, meaning it only behaves as a keyword in certain situations, which is why you can still use it as a variable name, but it's used as a keyword in that particular context. Right, pattern matching with instance of and records. So we discussed records earlier on. So we can do pattern matching with a record, because remember, records are just a special form of class. So here we can say, okay, we've got a record, our point record that we had before, double X, double Y, that's all good. Now we can say, let's create a method called Pythagoras, takes an object reference, and then we test to see if O is an instance of point P. If it is, we want to extract the values of X and Y so we know where this point is. So we get our X and our Y, and then we can calculate the hypotenuse as being the square root of X squared plus Y squared. Okay, this is all very good. It works. So we're doing pattern matching with instance of to get the pattern matching against point, and then referencing the pattern variable to extract the values, and everything works nicely. So this is good, but we can do better. We can use record patterns, which were introduced in JDK 19. Now this is interesting because it's an example of what's called a deconstruction pattern. There are actually several different pattern types. So you can have constant, which is what we used to use in switches where you had case and then a constant. We have type patterns, which we've talked about extensively. And now we're talking about a deconstruction pattern. Deconstruction pattern is where you're not just matching against something, but extracting information at the same time. Now, this only works with records. You can't use it with other objects. So now what we can do is we can simplify our Pythagoras code by saying test if O is an instance of point, but rather than just saying point as the type, we'll give it the record declaration point double X double Y. And that way, we can then simply use the values that we've extracted for X and Y by the deconstruction of that and have the compiler generate the code, which will give us the values of X and Y as pattern variables. And then we can use them in the code there. So we just do X squared plus Y squared. We don't have to do the extraction ourselves. Now, one thing I will say about this is that you cannot combine a deconstruction pattern with another pattern variable. By that, I mean you couldn't have if O instance of point double X double Y P and have P as the instance variable, pattern variable of that point. The reason for that, they did initially allow that to happen, but then it covered that there are certain situations, and when is one of them. When gets very confusing, because if you said if O instance of point double X double Y when, give it the variable name when, and then you try and use that it gets to the point where you end up with a situation that the compiler cannot produce a single version of the code. There's two different ways it can be interpreted. It becomes ambiguous. That's the word I'm looking for. So they don't allow pattern variables for the type when you're using a deconstruction. So let's take this a little bit further, because patterns are also composable. You can compose them together. Let's create an interface called rectangle. We'll use our point record again, so double X, double Y. We'll introduce an enumeration for color, red, green, and blue. And then we're going to have two new records, a color point, which will take a point and a color, very logically. And then we'll have a color rectangle, which will take a color point being the top left and a color point being the bottom right. And just to make our lives easier, we'll implement the rectangle interface. So now what we can do is we can say, let's have a method which is print color, and we'll pass in a rectangle. So it's an interface, so we could have other things that implement that interface. Now we can do if our instance of color rectangle, and we can use deconstruction to say color point top left, color point bottom right. So we're doing the record declaration of our color rectangle, and then we can print out top left dot C. So we can call the C method on the top left pattern variable, and it will work quite happily. But we know that top left is a record as well. So let's compose that, or compose that into separate patterns. So now what we can do is we can say, if our instance of color rectangle, so we give the declaration for color rectangle, but then we can put the declaration for the color point in there. And interestingly, we don't have to use the same variable names if we had a different declaration outside of this. So we can change the variable names as much as we want, which is because then we can simplify it and say color point P, color C, and color point BR as the bottom right. Now we only have to print out C. So we've got access directly to the one thing that we want to use. But of course, point is also a record. So let's compose this. And let's say print out top left X of a rectangle. And then we can say if our instance of color rectangle, color point, but then we've got point in there. So we point double X double Y to give the record declaration for that. And then we've got color C and color point BR. And then we can just print out X. Now, at this point, you're probably thinking to yourself, well, that's really good, but it's not making my code simpler, is it? It's actually making it harder to read. So where is the advantage of this? Well, the advantage comes because you can use other things. You can combine this with other features in Java. If we look at this, clearly we're only actually interested in X in this particular example. So really, everything else that's declared here, we don't care about. What we can then do is we can use local variable type inference introduced in JDK 10. So now we have the var keyword, and we can simplify our code a bit here by using that. And we can simply say color rectangle, color point, and then simplify the types and let the compiler figure it out for us, so long as we don't have any ambiguity. Var X, var Y, var C, var BR. So that makes it a little bit easier, but still, we can do better. So then they introduced the idea of unnamed pattern variables. And this is where, again, this is another form of pattern matching, which is where we have the unnamed pattern match, where we don't care about something. And this, we can basically say, use the underscore character to represent something that we don't care about. And now it looks like this. So we say instance of color rectangle, color point, var X, because we do actually want X, so we need a reference to it because we want to use it to print it out. But the other things that we don't care about, we simply put an underscore there to indicate that there is something there. So we've got to be able to match against the signature of that record. So we know that there's more than one thing stored in it, but we don't care what it is. We're not going to use it. We don't need a reference to it. So use an underscore so the compiler knows that it's looking for a record called point with two things in it, and a color point with two things in it, and a color rectangle with two things in it. So it will all work out in the end. But it does simplify the way that it works, and it allows you to reduce the amount of bloat you have in your code here. So yeah, we've got no interest in those, so we'll basically ignore them. Unnamed pattern variables. So this was also introduced. So this is again using the underscore. So here we can use it in a switch statement as well. So we can do case string, and then because we would typically have a pattern variable there, we don't want to use that pattern variable because we're just going to print out it's a string. So we can replace the pattern variable with an underscore. Same with color, same with float. That's probably less of a has less sort of benefit to it because you could just use a single letter variable name, and because of the scope, it doesn't really matter how many times you reuse it or anything like that. Primitive types in patterns. This was introduced in JDK 23, so this is the most recent thing that they've done in terms of pattern matching. What they've done here is to extend the way instance of and switch handle primitives. So in the example I showed you earlier with the pattern matching for switch, I said that you couldn't use a primitive in that switch. Now you can. So what we can do is we can do things like this. So we can say byte x equals 128. If x instance of int, print out we have an int. If x instance of int, and then we can add a pattern variable as well. And then we can say we have an int with a value and then use I. So we can use it in two different ways. Either as the type that we're going to match against or type with a pattern variable. Right. So this can get complicated. So you need to be careful about how you use it, because you can do things like this. So we've got a value of type float that we're getting. We're going to switch on that float, and we're going to switch on the value. And then we can say, okay, case where we have a constant, 0, f, then we want to return 5 float. But then we also want to have a situation where we're saying, okay, we've got a float, but we're going to have a guard added to that. So we'll say, if it's a float, when x equals 1s, 1 float, then return 6f plus x. The reason we would do that, I guess, actually, I have no idea why we would do that, because you could do it in many different ways, but I guess it's an example for my slide. And then you can have float x on its own, because, of course, we have to be complete. So we have to deal with all possible values of the float. So if it's not 0 or it's not 1, then we'll print out, or we'll return 7 plus x. There are some quite detailed rules. So I put that here. There are some quite detailed rules on how exhaustiveness works in this scenario. I would suggest read the JEP 455, which gives you a lot of detail about how all of that works, because it does take a little bit of thinking about. Right, primitives in Switch is, again, where we can do some interesting things which I don't recommend. Here I've got test_, which takes an object, and then I'm going to switch on O. I'm going to have a case for integer and a pattern variable called I, and I'll print out an integer. Then I'm going to have a case for primitive byte. So integer obviously is the wrapper class for integer. So I'm going to have a case for primitive byte with pattern variable B, print out byte, and then a default which will print out something else. Let's look at some examples. So what would be the result of test_, where we pass in integer.value of 42? Anybody want to guess what that's going to do? Did I hear integer? Yes, I hope I heard integer, because the answer is integer. Because literally we are creating an integer object using the value of, and then passing it to test_. So it's going to match against integer. There is no question about that. We have an integer object, we match against it. What about if we go test_, 42? Trying to pass a number to this. So, okay, let's have a show of hands. So who thinks we're going to see integer? Okay, right, reasonable number of people. Who think byte? Okay, a few people. Who thinks something else? Okay, well, that's fairly evenly split. Okay, the answer is that we will see integer. Why will we see integer? Auto-boxing. Because remember that the method signature says that we have to pass an object. We can't pass a primitive as an object unless we box it into the wrapper class. So that's what the compiler will do. It will say, oh, you've got a number, you need an object, so it will auto box it into a wrapper class. But the interesting thing here is, what does it box it into? 42 is quite a small value. 42 will fit in a byte. So why does it box it into an integer and not a byte? And the answer is auto-promotion. So if you look at the way that Java is defined, yeah, and this is where we get into those like little edge cases, and I can see you kind of like shaking your head. You get into these little edge cases where you get auto-promotion, where any number that will fit in an integer, regardless of how small it is, will be an integer. If it doesn't fit into an integer, it'll be a long. But in this case, it auto-boxes into an integer, and therefore we see the value integer. Right. What about if we do test_byte.value of, and then cast 42 as a byte? You actually have to cast 42 as a byte for that to work, which is a little annoying, but that's the way you do it. So, show of hands, who thinks we'll see byte? Who thinks we'll see something else? Okay, the answer is definitely we will see byte, because we're passing in a byte object. So we're creating a byte object, instantiating it using the value of method, and therefore we get a byte. Okay, I think I've got one more here. Right, okay, so what about if we do this? So we pass in, so we call test_, and we explicitly cast the value 256 as a short?
Dividing is nothing.
Right, so we're going to have show of hands here. So who thinks integer? This side definitely going for integer. Who thinks byte? Oh, okay, a few people, yeah. Who thinks something else? Okay, right. So and there's a few people who didn't vote. Right, so the answer is something else. Now, the reason for that is that, again, one of the sort of like little sort of fiddly bits in Java is that if you pass that as a short, when the compiler does the auto boxing, because you have cast it as a short, it will respect that so long as it fits into a short, which, you know, it have to do. So it will then box it into a short object. It won't auto promote it. It will respect the fact that you've cast it as a short and then box it into a short, which doesn't match against integer, doesn't match against byte, and therefore will work. Actually, yeah. So I should have said this before because I didn't explain this well enough, did I? We're passing in a byte object, but it's unboxing that happens in this case. So it says, okay, you passed in the object, and it will unbox that byte to give you the byte value, and then it will match. So sorry, I didn't make that clear enough in that one.
What? More than
No. 256 is more than a byte. Byte is 255, and I deliberately chose that number. And what's interesting is if you do it with a number that's smaller than 200 or 50, so if you do it 255 or less, it still will say something else. So it will still respect the fact that it has to be a short, and so it will auto box it into a short.
What is the average choose about to
So say that again. So the question was, can you have an integer type reference and an integer primitive reference? I think the answer to that is no. I'd have to check it, but I'm pretty sure you can't do that because you would, because you're basically representing the same thing, because you can only pass in either a primitive or an object. And so auto-boxing and unboxing will always generate the same thing. So I'm pretty sure you wouldn't be able to do that, and the compiler would reject it. But again, there's lots of these little edge cases that kind of catch you out there. Right, just to summarize then, pattern matching is a powerful set of language constructs. There's a lot to take in there. It definitely simplifies certain tasks. It's very good for that. Generates less boilerplate code, makes your code more declarative, should be therefore easier to read. There's also some interesting work going on in terms of, even though this looks a lot like syntactic sugar, there's some work going on where we could improve the efficiency and therefore the performance of the code that's generated underneath. So there's some definite work going on there. Some of these features have already been included. There is more in the pipeline. I would expect to see more coming out later. There was a proposal for doing deconstruction patterns with arrays, but they kind of added that as a proposal, but then they never actually included it, and they kind of backed out from that. But there are other ideas for things to do with more pattern matching that will happen in Java. Just one question. So before you came to my presentation, who had heard of Azure? Okay, so half the audience. So this is my one marketing slide. I'll give you 15 seconds of marketing. We basically do Java, and we have two products. Platform Core, which is a replacement for Oracle Java, drop-in replacement, built with OpenJDK, does exactly the same thing. It's just a whole lot cheaper. Platform Prime is probably the more interesting one. That's high-performance Java. So we use a different garbage collector that's truly pauseless. We have a different JIT compiler, which generates more heavily optimized code. So if you're running things like Kafka, for example, we can do 43% more transactions per second just by changing your JVM. Nothing else. So if you're interested in any of that stuff, feel free to come and talk to me or have a look at our website. That's the end of my marketing message. So with that, thank you very much.